So we are going to look at the full orthogonalization method. This is a projection method. Remember, when we talk about a projection method, we have the search space, which is typically denoted with a K, and then we have the orthogonality space, which is typically denoted with an L. In this case, the search space and the orthogonality space are going to be the same space. Now, in the case, this method works whether or not A is a symmetric matrix. But in the case where A is a symmetric matrix, we saw that this method equates to minimizing minimizing the difference between our guessed solution, that is the solution that we have guessed, or the solution that this method creates, and the actual solution in the norm induced by the A inner product. This interpretation really only makes sense when A is a symmetric matrix, but this method works whether or not A is a symmetric matrix. Now, the other thing is that this is not one of the main methods. We're going to look at this method, and it's going to lead us to the GMRES method. But I think understanding this method is a little bit easier. If you understand this method, then it's a little bit easier to go from that than the GMRES method, than to go from nothing to the GMRES method. So it's kind of like this is just a stair step. In a sense, it's not completely necessary to get to where we want to go, but just like understanding Jacobi, then Gauss-Seidel, then SOR is a lot easier than going from nothing to SOR. There's something similar at work here. Okay, so for the FOM method, for the full orthogonalization method, we're going to have the following. Our subspace K is going to be equal to the Krylov space. So, okay, this chalk is now, hold on. Let me just run this. All right. So it's going to be the span of the following. Okay, that chalk is dead. The span of R naught up to a m minus 1 R naught. In other words, we're saying that K is equal to the mth Krylov space, and that's also going to be our L. And remember what we're trying to do here. We're trying to find a delta. We want to look at B minus AXM. We want this to be orthogonal to K, and we want XM to equal X naught plus delta, where delta is going to be in our search space. So that is normally L, but L is equal to K, so we're going to write it like this. Now this orthogonality condition, since XM is equal to X naught plus delta, the computation that we've done several times, B minus AXM is simply R minus A delta. Okay, now we want R minus A delta. These two things are equal. We want R minus A delta to be orthogonal to K, and we want delta to be, we want delta to be in K. So we can write this in the following way. If delta is in K, then it is a linear combination of the Vm vectors, because the Vm vectors here form a basis for K, so it would be a linear combination of those vectors. In other words, it can be written as a matrix vector multiplication, Vm times Ym for some Ym in m-dimensional Euclidean space. Okay, so we want this to be orthogonal to K. So I'm going to rewrite this up here. So we want R naught minus A Vm Ym to be orthogonal to K. And if we write out what this means, well, it means if I do the inner product of this with V1, it's equal to 0, If I do the inner product of this with V2, it's equal to 0. If I do the inner product of this with V3, it's equal to 0, and so on and so forth. So I can write this as Vm transpose times R naught minus A Vm Ym is equal to 0. Okay, and now this one equation sort of encapsulates everything that I want. I want delta to be in K, so Vm Ym, that's my delta. This is delta, and it's a linear combination of the columns of Vm, which form a basis for K. So we see that this is in the space K, and I want this difference to be orthogonal to K. And now what does this mean? Vm transpose, when you do this, this is a matrix, this is a vector. When you do this product, the first entry of this matrix vector product is going to be the dot product of the first row of Vm transpose with this vector here. Well, what is the first row of Vm transpose? It's just the vector V1, but on its side. So V1 dotted with that, if that's equal to 0, it means V1 is orthogonal to this. And similarly, all the way down to Vm. What is the mth entry of this going to be? Well, it's going to be the last row of Vm transpose dotted with this vector here. In other words, it's going to be the vector Vm dotted with this vector here. So the last entry of this matrix vector product is 0 if and only if this is orthogonal to the vector Vm. And in general, the jth entry of this matrix vector product is going to be 0 if and only if this vector is orthogonal to the jth vector, to the vector Vj. Okay, so I'm going to rewrite this. And so now what we have is we want to solve Vm transpose A. If you distribute the Vm transpose, you're going to get Vm transpose A Vm Ym is equal to Vm transpose R naught. Yeah. Now we have a formula. Vm transpose A Vm is just equal to HM. So on the left-hand side, we're going to have HM Ym. Now what do we have on the right-hand side? Because it looks like we're going to have to be doing a matrix vector product here. But we don't actually have to do that. We know what Vm transpose times R naught is. Why is that? Well, recall that the vector V1, what is the vector V1? It's just equal to R naught divided by its magnitude. So V1 is equal to R naught divided by R naught. Or another way to write this is we have Vm transpose. R naught is simply V1 times the magnitude of R naught. So we're going to have the magnitude of R naught and then V1 here. Okay, but now remember V1 is one of the vectors in the Vm matrix. And so there's this orthogonality and normalized. Orthonormality. I don't know why I'm having trouble talking. Okay, Vm transpose times V1 then, well, what is the first row of this matrix? It's just going to be the first column of Vm transpose, which is V1, dotted with V1. So it's going to be 1. The first entry of the Vm transpose times V1 is going to be 1. What is the second entry? Well, it's going to be the second row of Vm transpose dotted with V1. In other words, it's going to be V2, the inner product of V2 with V1. Well, V1 and V2 are orthogonal, so that's going to be 0. And it's going to be 0 for all of the other entries, all the way down to the last row of this matrix. The last row of this matrix is the vector Vm. By construction, Vm is orthogonal to V1, so therefore it's going to be equal to 0. And so this is just going to be equal to R naught times E1. So the equation that we started solving is AX equals B. We look in this search space Krylov, this Krylov space, we just restrict our attention to that, and the equation that we end up solving is just HMYM is equal to this here. Okay, so let me write that now. So what we get is that we want to solve HMYM is equal to R naught E1 like this. Now, notice what we also need to do here is when we are doing these iterative methods, we need to compute the norm of the residual, or we need to compute some measure of the size of the residual. So in other words, typically, part of this process is going to be computing something like, let me use a different color here. It's going to be computing something like b minus a x in, and then measuring the size of that either with the infinity norm, which is what we've done in the past, or as we're going to do today, we're going to measure it in the 2 norm. So b minus ax in, well, we already saw that we can write this as r naught minus a delta, or minus a vm ym. Okay, so again, where ym is the solution to this problem up here. Okay, AVM, we have a formula for AVM. It's given by this up here. So what this is, we're going to have R naught minus, is going to be AVM YM. So we're going to have VM HM times YM minus this, HM plus 1, HM plus 1, M, V, M plus 1, EM transpose. Times YM. Okay. But look at what's going to happen here. What is VMHM times YM equal to? Well, HM times YM is R naught E1. So we're going to have R naught minus VM R naught E1. And then minus this part here, H n plus 1 m, V m plus 1, EM transpose YM. Now what's happening here? When you do VM times E1, all you're doing when you do VM times E1 is you're just getting the first column of VM. But what is the first column of VM? The first column of VM is just V1. So this is going to be V1 times the magnitude of R naught. Well, what is this? Over here, V1 times the magnitude of R naught is just R naught. So this right here is just R naught. And so what we're left with is this vector right here is 0, so we're just left with this vector right here. And I'm going to write that up here. So B minus AXM, B minus AXM is equal to minus H m plus 1 m, and then we're going to have V m plus 1 EM transpose YN, like this. Okay, so now this tells us two things. One, it sort of gives an indication that the direction of the residual is going to be in this Vm plus 1 direction. But another thing that we can do here is if I want to compute the norm, if I want to compute the Euclidean norm of both sides of this, if I want to compute the Euclidean norm of both sides of this, that is just the standard 2 norm, then what am I going to get here? Well, I'm going to get the absolute value of H m plus 1 m. Okay, what's happening over here? Well, Vm plus 1 is a unit normalized vector, so its magnitude is equal to 1. Em transpose times ym, what's happening there? Well, this is just going to give us the last entry of yn, basically. So we could write this as the absolute value of em transpose times yn, and we know that means it's the last entry of ym, because em transpose, the dot product of this with ym, this is all zeros until the last entry, which is 1, and so you do this dot product here, or this em transpose times yn, which is the same as the dot product. You're just going to get the last entry of yn. Okay, so this is what we have then. So what it tells us is that the norm of the residual, and then we're doing the absolute value twice here, so you can just do it all in one absolute value if you wanted to. So kind of write it like this. All right, it's going to be the absolute value of the bottom right entry of the A matrix, and then the last entry of the yn. So in other words, if we want to compute this is exact. This isn't like less than or equal to. This is exact. So in other words, to compute the residual, we don't actually have to literally compute b minus axm, and then this is going to be a matrix vector product. We're not going to have to do that. We're not going to have to do this difference, and we're not going to have to compute the norm. It's just literally equal to this number right here. And so it's a much easier way to compute the residual. All right, so now this is going to lead us to the FOM algorithm that's going to use this Arnoldi orthogonalization. And as we will see, it's going to be very similar to this right here. And in some sense, it's just going to be this algorithm with like a wrapper around it. There's going to be the FOM method is basically going to be this Arnoldi algorithm wrapped in some other stuff. Anyways, you'll see, if that doesn't make sense, you'll see what it means in just a moment. But you should copy these formulas down because I'm going to need to use this board space. So there, you can pause the video and copy them if you want. For the FOM algorithm, I'm going to have to, there's not enough space here for me to write everything in one column. So I'm going to sort of try to split things up. The left-hand side is going to be like the initialization step, and the right-hand side is going to be sort of the main computational loop. So for starters, we're going to, I'm going to detail this algorithm slightly differently than the way it's in the book. I'm going to detail it in a way that's going to be a little bit more consistent with how we're going to implement it in our Python programs. Okay, so we're going to have these initialization steps. Let me even write this in a different language. Or sorry, not a different language, a different color. Okay, what color do I want to use here? Let's see, orange. Let's see if orange is going to work. So for step one, we're going to make two zero matrices. V n plus 1, the dimensions of this matrix are going to be n by m plus 1, so n rows and m plus 1 columns. In other words, it's going to be the basis for, it's going to contain the basis vectors basically that this Arnoldi step is going to make. But we're going to initialize it to be equal to 0. We're also going to create the HM bar matrix. HM bar is going to be m plus 1 by m, and initially we set HM bar to be equal to 0. Okay, that is the first sort of initialization step. The second initialization step is we are going to compute R naught is equal to, wrong way, b minus ax naught. Now this requires an x naught. So the user of so there are two legitimate ways to do this. Either the user picks what x naught is, or the algorithm picks what x naught is. It just sort of depends on your perspective here. And we're going to discuss why there are legitimate uses for both of these. It just sort of depends on exactly how you implement this algorithm. There's going to be some other details that we discuss as well. And then you're going to set the first row of this, the first column of Vm plus 1, not yet, sorry, beta is going to be equal to R0, the norm of R0, beta is the norm of R0. I don't really like using beta for something like this because it doesn't really come up a whole lot other than right here. Anyways, So beta is equal to R naught, and V1 is equal to R naught divided by the norm of R naught, in other words, R naught divided by beta. Okay, and then the final initialization step, which really isn't mentioned explicitly in the algorithm in the book, is we're going to set the first column of Vm plus 1. We're going to set the first column of Vm plus 1. So like in Python notation, we would have a colon here and then 0, telling us that all of the entries of this means the column. So the column is going to be 0. The first entries are going to be set to equal to V1. Now I'm not going to write it like this. I'm just writing it like this to sort of let you know about how it's going to be in Python. The issue though is that if we mix the Python indexing, which is 0 index, with the mathematical indexing, which is 1 index, is going to lead to confusion. So instead of writing that formula, I'm just going to say first column of Vm plus 1 to V1. Okay, so in other words, when we step into the main computational phase of the algorithm, we have a matrix Vm plus 1. The first column is going to be V1, and everything after that is going to be equal to 0. And then our matrix H here is also going to be all zeros as well. And then we're going to start filling this in as we go along. Okay, so now we get into the main computational part of the algorithm. Step 3 is going to be the loop. This is going to be the outer loop. So for j equals 1 up to m, we're going to do the following. We're first going to compute wj, which is going to be a applied to the vector vj. So it's like this step over here, this step right here. Wj is going to be equal to a applied to the vector vj. Now we're going to have our inner loop. For I equals 1 up to j, we're going to do the following. We're going to form hij. This is going to be the inner product of wj with vi. And then we're going to say wj. We're going to set the new value of wj to be the old value of wj minus hij vi like this. Okay, so this is sort of standard computer update notation. This is not an algebraic equation saying these two things are equal to each other. The colon here means I'm setting wj to be the right-hand side. Okay, or in more succinct notation, it would be wj minus equals hij vi. Okay, so once we do that, we're going to end this. Okay, now we're finally at the end of the inner loop, so we're back to the in the outer loop. We're going to compute the final hj plus 1. So hj plus 1j is now going to be equal to the magnitude of wj. There's an asterisk here that I will get to in a moment. Item 10 is going to be vj plus 1 is going to be equal to wj over its magnitude this is j plus 1j. And then I'm going to use this notation here, meaning we're going to store that in the matrix Vm. So the j plus 1th row of Vm is going to be equal to vj plus 1. Okay, 11 is going to be the end of the outer loop. And then in step 12, we're going to solve HYM is equal to beta E1, and then return, return XM equals VM YM plus X0. Sorry. I just needed my board to be like a couple inches longer. Okay, but I think that's clear. And then we can compute the residual as well. So this algorithm should also return the residual, and we saw how we can compute the residual without actually having to do the B minus AX. Okay, a couple of things that need to be pointed out here. This case right here, WJ, there's no guarantee that this is going to be non-zero. So whenever we are, if you think back to Gram-Schmidt, whenever we have a basis of vectors, so the reason I want to go back to Gram-Schmidt is because this is just a modified version of Gram-Schmidt that solves a couple of problems. One, the problem of computing powers of the matrix M in a numerical stable way. And two, this gives us a basis, this gives us a matrix with respect to which A has a nice form. Anyway, we've talked about that before, but this is just a modified form of Gram-Schmidt. If you think about what's happening in Gram-Schmidt, you're given a basis and you systematically orthogonalize the next vector to the ones that come before it. Okay, so then what happens is, since the vectors begin as a basis in the Gram-Schmidt universe, or in the Gram-Schmidt algorithm, you begin with a basis. In other words, the vectors are in particular linearly independent. But there's no reason at all a priori to think that the vectors R naught, A squared R naught, all the way up to A minus 1 R naught are going to be linearly independent. Okay, there could be some vectors, in fact there are some vectors where A to the power of K times that vector is going to be equal to the 0 vector. Okay, or maybe some polynomial in A times R naught is going to be equal to the 0 vector. And let's say that we have a situation where there is a kth degree polynomial, and there's a kth degree polynomial, and P of A times R naught is going to be equal to 0. Well, what this means is that once we get up to A to the power of K times R naught, we're just going to get the same Krylov space over and over again. Okay, so there's a danger. What can happen is the following. So let me write it up here. It's actually not a danger. It's kind of a good thing. If P is a k degree polynomial, and P of A times R naught is equal to 0, then what we're going to have is the Krylov space with that k plus 1 is just going to be equal to k sub k. So in other words, once we hit that vector, everything after that is going to be in the span of everything that came before. In other words, we don't have in other words, we no longer have linearly independent vectors. Now, this is great because what it means is that in that Krylov space, we actually have the actual, not a projection of what we want, but the actual thing that we want. And so we can solve the problem exactly. And so in this case right here, if h j plus 1 is equal to 0, we're going to set m equals to j, because what this means is the projection of a j plus 1, or sorry, if you look at a j plus 1, we have subtracted off the projection. What this is doing, again, Gram-Schmidt modification, we're looking at aj plus 1 and looking at its projection on the previous j vectors, v1 through vj, and we're taking that projection and subtracting it off of aj plus 1. But if a vj plus 1 is already in the linear span of v1 through vj, then that's just going to be equal to 0. If a vector is in a span of the vectors, and you do that vector minus projection onto that span of vectors, all you're left with is a 0 vector. Okay, so if a vj is in the linear span of v1 through vj, wj is going to be equal to 0. So we're going to set m is equal to j, and we're going to go to 12. We're just going to return this ym here. In other words, this xm is going to be the exact solution to the problem. So these are called happy. This is a breakdown in the algorithm, but it's called a happy breakdown because it leads us to the exact solution. Of the matrix vector problem. Of course, we always have to deal with the we don't have precise arithmetic. But aside from that, it's going to lead us to the exact solution. It's going to give us, this algorithm gives the exact solution. Now, while there is no reason to believe a priori that it won't break down, there's no reason to believe that it will break down either. In fact, sort of maybe to go against what I just said, just in a combinatorial point of view, if you have an n-dimensional space, there are n choose m-dimensional subspaces. And n is typically going to be much larger than m. So there's going to be a lot of m-dimensional subspaces. And the fact that we've just happened to stumble across the one that contains the solution is not, maybe it's not likely. Okay. There's the probabilistic thing I'm not going to try to get exactly, but I think combinatorially what I'm saying sort of makes sense. So the bottom line is there's no reason to expect there will or won't be a happy breakdown. If there is a happy breakdown, great. If there isn't, then we just do this method. Okay, now how do we actually implement this method? So I want to note a couple of different things about this algorithm than the other iterative algorithms that we've looked at. So the other iterative algorithms we've looked at, we have a guess, we update that guess. Then we forget about our initial guess, we update that new guess. Then we update that new guess, and so on and so forth. But that's not exactly what's happening here in the way that this algorithm is presented. No, what's happening here is we start with a guess x naught, and we update it once at the end. The iterative nature of this problem in this formulation here comes from applying this Arnoldi algorithm in an iterative way. That's one way that the iterative method comes from. The question that we have to ask when we implement this algorithm is, as this algorithm is stated, we are given m. Like, this algorithm does not choose what m is. This algorithm has m already built into it because that's how we know when to stop. So how can we choose what m is? Well, there's a couple of ways that we could do this. We could just, based on some theoretical considerations that we're not even going to think about, maybe we can find a value for m. Maybe we pick m to be 200 or 100 or something like that. Maybe we do something like we pick m to be whatever the size of the space is. Maybe we begin by making m be whatever the size of the space is. So it's equal to n, and maybe we're going to go through this algorithm for, like, we're going to go through m from 0 to 10, and then we're going to check the residual. If the residual isn't what we want, we're going to go from, m goes from 11 up to 20, and if that residual isn't what we want, we're going to keep going, and so on and so forth. And so we sort of do this algorithm for, like, blocks of m, okay? I think that makes sense. So like we would, I know what I'm trying to say makes sense. Whether or not my explanation makes sense, I guess, depends on whether or not you understand it. But what I mean is, we could say, let's say m is equal to 10. We're going to compute this. If the residual is within the tolerance that we want, we'll just return xm. If not, we'll just do this for 10 more of these algorithms. We'll just sort of go again from 11 to 20. And if that residual is what we want, then we'll return. If not, we won't. And we'll just do this over and over again. Okay. And now, how long are you going to do this for? Well, there's an upper limit. It's going to be equal to n, because once you get up to n, you have the entire space. And again, probabilistically, you're probably not going to have to go up to n. You're probably going to have a happy breakdown before them. The question is when. So the other method, so we're going to implement this algorithm here, and we're going to have to, in the implementation, figure out these details about what m should be. Okay. But what we're going to see then is when we get to when we get to other methods. Again, this is not going to be so much important for this method because this is not one of the primarily used methods. But we're going to do something called restarting. So what this is we might pick m is equal to 10. We're going to do this up to m is equal to 10, and we're going to have our vector here x sub n. And now we're going to take that as our new vector and restart this algorithm, again with m is equal to 10, but x naught is going to be the vector from the previous step, or from the previous cycle. Okay, so this is what I meant in the beginning when I said there are two reasonable things. Either this algorithm picks what x naught is, or the user picks what x naught is. We could sort of implement this as one cycle of an FOM, and we get the answer. If the residual is what we want, we don't do another cycle. Otherwise, we take that as our new starting value and do a cycle of this, do this algorithm. If that residual is what we want, then we stop, we don't do another cycle. If not, we do another cycle, and so on and so forth. Okay, but we're going to implement this numerically, and we're going to sort of do some experiments to see, what m needs to be and stuff like that. And for the final project, we'll have something. This algorithm won't be part of the final project, but for the final project, we'll sort of maybe have some restarting implementation and stuff like that. Anyways, this is the basic outline for the algorithm. We're going to see how we can implement this in code during the lab. You can already see the homework is posted. And you can kind of see maybe how these two things are going to go together. The Arnoldi algorithm together with its application to the FOM algorithm. Okay, so that's it for this video. In the next video, we're going to look at the GMRES method.